Okay, today we'll see the main part of deep learning, that is the introduction to neural networks. So basically, you might know that human brain consists of neurons. So basically, the neural network models that we use are inspired by the neurons in humans. So generally, neuron consists of a center cell dendrites going through and some information going through like this. So what happens is these dendrites are connected to some other neurons, and they are connected to some neurons like this. So there is a chain connections available of neurons. So each neuron will take information from its surroundings. Uh, it takes information from its surroundings and does some kind of processing within it. And this processing will uh, create a response that will go to the remaining neurons. So information will be passed through the whole system like this. So this is general structure of and natural neuron. So artificial neuron is inspired from this. So previously we saw using linear regression, we had a model called y dash equal to some x plus c, right? If there are more than one x values or more than one feature, we have m1 x1 plus m2 x2 plus c. So depending upon number of input features, we have different parameters. So here we can call those parameters as weights. So these weights will be changing with each update. So if you remember, some weight after one update, W1 is equal to current weight uh, minus or plus, you can say plus alpha times uh, the derivative that we get here. So this alpha is the learning rate, and d is the cumulative loss or the cost that we achieved in the previous step. So after doing this step, we will get a value for the new W. So after doing this process many times, we'll reach a local minimum. Similar to that, let's consider a neural network. So we have here the same function will be there. So y dash is w1 x1 plus w2 x2 plus w naught. So suppose we have two features x1 and x2. For each data point, we have two features. So let's take one feature x0, that will be equal to 1 always. This part is just for convenience. So previously we had a constant c, right? C into 1, we'll just keep that 1 as our feature, pseudo feature, you can say. So now these features will be multiplied their corresponding weights, and after the multiplication, we have a summation along them. So this is the structure we previously saw. So now what we do is, instead of just saying the output is our prediction, what we do is we take the output from here. We take the output from there and send it to a non-linear function. So some non-linear function. Uh, Generally, non-linear functions are sigmoid or ReLU or things like that. So what a sigmoid function does is it will convert all any value from minus infinity to plus infinity. So the graph is like this. So any value will go like this. So this is an asymptote, and here is another asymptote. So any value that we give in x will be converted to a value between minus 1 and sorry, this is plus 1, and here we'll have minus 1. So if we sometimes we can also convert this and say that it can be converted to any value between 0 and 1 just by subtracting minus 1 to the whole thing and dividing by 2 we can convert it between any value between 0 and 1. So this is the basic non-linearity. One more thing is a ReLU function. ReLU function is nothing but if the value is less than 0 or a negative, it will return 0. Or if it is greater than 0 or 0, it will remain same. It is some kind of non-linearity. So by applying this non-linearity, we will convert most of the information into uh, uh, a format in which we can do a bit more processing on it. So here, this whole part, we can consider as a single neuron. Say, yeah. This whole part we can consider as a single neuron, and the output of this part, this the output here that we get here is our y dash. So now previously we had an output here after the summation, right? Now we'll have the output here. Just we are just adding a non-linearity here to the output function in linear regression. So this single part is called single neuron. Now we can add more neurons to it. Let's see how we can add more neurons. So let's delete this code part. So say we have our data here, those x values. X0 will be 1, x1, x2, x3 till xn. Any number of features we may have. So now let's have 3 neurons. So what does each neuron consist of? Each neuron will have weights and a bias, right? Bias is this part. So if we consider x0 as a feature, we can directly put there are as many weights for each neuron as there are number of features here. Or else if we can put a single neuron called bias here. It doesn't matter about the representation, but here for this class we'll consider that there are n plus 1 features, and there are n plus 1 weights for each feature. So each neuron will have some weight, where same number of weights. So here say there are 3 here. So for this neuron, we'll have w, say it's a 0th neuron. So we'll have w1 of 0, w2 of 0, w0 of 0. These will be the weights inside these. There are 3 weights inside this, and say this is one green neuron. So green neuron also will have some different weight, w1 of green 0, w2 of green 0. Or we can say if this is the first neuron, we can say 1 here, w1 of 2, w1 of 0. And for blue, for this, let's say this is the third one. We'll have one here. Sorry, let's say this is the second. So this is the 0th neuron. This is the first neuron, and this is the second neuron. So for each, we'll have uh, 3 weights. This is 2. This will be 2. So will be 2. So here we'll have 3 weights. Here we'll have 3 weights. Here we'll have 3 weights. So all these points will be connected to this, and all similarly to this neuron, and similarly to this neuron. So in each step, what happens is all these x's will be multiplied with the w's inside them, and will be give us a summation output, or by adding all those products. This neuron will also give us the summation of all the products. This will give us the summation of all the products. Now we'll take the summation into a non-linearity function, say some sigmoid function or some ReLU. It will be sent, the information will be sent into some non-linearity. So this non-linearity will be done, and then we'll have an output here. Now we'll add these outputs, and we'll have a final prediction here. So this y dash is the summation of all these sigmoid activation functions. So suppose there are, this is a thing that will come. So here we see. So initially we have some data that goes in, will be multiplied with the weights. So these are the weights: 0.7, 0.6, 1.4. These will be the weights, and the incoming will be the data. These will be doing some multiplication, and then we'll add all of them together, and then it will be sent into a non-linearity. So this bias, since we considered W0 as X0 as 1, it will be bias will be one input like this. If we did not consider this, we at the end will add the bias to the sum. And then it will be sent into some non-linearity, and that will be our output. This is for one single neuron. So here you can see some different activation functions. So some sigmoid goes from minus infinity to infinity. It will convert information to 0 to 1. Tanh will convert information from -1 to 1. ReLU will convert, if it is negative, it will return 0, or if it is positive, it will return the same value. So there is some leaky ReLU, it will return a very small negative value if it is negative, and the same constant positive value if it's positive. So max output is just the maximum output from the summation. This one we do not use much. LU is also some kind of thing that is continuous. These two functions are ReLU and leaky ReLU are not differentiable at x equal to 0, but LU is a function that can be is a continuous and differentiable function that does almost the similar thing as ReLU. So let's see the structure of a multi-layer perceptron. So this one we can call single layer perceptron, since there is only single layer, right? So there is one, previously we saw single perceptron. Now this is a single layer of perceptrons. So perceptron is nothing but the neuron that we drew. So this is a perceptron, this is a perceptron, this is a perceptron. All of them are in a single layer. So this is the sigmoid. You can also like combine these two together and call it as a single perceptron. So now this is a single layer perceptron. So information will pass through a single layer of neurons, and we'll get an output at the end. We can add, rather than this, uh, ra rather than this, if say suppose if we have some more neurons here. So there are say 3 more neurons. So after the sigmoid, information will be sent to all the 3 neurons. This is kind of an input for the previous thing. So here for these perceptrons we have input as our features. For this perceptron layer, we'll have inputs as the output of the previous layer. So a single vertical stack of the neurons is called a layer. And after that, after this, we can have an output. We can combine all of them together into a single output, um, or we can have two more neurons that can be considered as outputs. So this we can have two or many number of neurons as our output. So this part is one layer. This part would be another layer, and this the first part would can also be one layer. So the output layer sometimes is not the layers that are not output or input can be considered as hidden layers. So since we cannot will not see the information that comes out of this, we'll only see the output that we achieve here, and we see the input that goes in. So this is the input layer. This part would be the input layer. So yeah, this part would be the input layer. This part would be the output layer. So this thing in the middle is called hidden layers. We can add how many number of hidden layers as you like. And each hidden layer can consist of any number of layers, vertical stack of uh, perceptrons. So here you can see a large, these all are the input features. These are the first layer of perceptrons. This is the second layer of perceptrons, and this is the third layer. So this has three hidden layers. This is the output layer. So information will pass through them. It will go. It has some summation and some non-linearity, and out will finally get the output here. This you can see here. This shows a bit clearly how the data. This is the data, and these W's are the weights in the perceptron. And after multiplication, we'll do a summation, and we have an output. So after that, this will finally give us a classification output that can be divided into two different groups. So there are two different distinct classes that we can classify the data into. Here the data is there are two cats and dogs. There is a distinct line that can be drawn along these points. So previously, without the non-linearity, we can only draw a single line, right? So that will only create a line that divides our points in some high dimension uh, space. Here, by using this non-linearity, we can create a surface that is not a straight, but we can have some contours attached to it. This will help us to classify with more accuracy. There is one good tool by Google TensorFlow called TensorFlow Playground. You can go through this. So suppose we have this kind of data. There are two distinct classes, and say we are giving x and x1 and y1 are features. We can add number of neurons or subtract number of neurons. We can even add a different layer of neurons. So here, let's say these are the different layers that we have, and here we can start our training. So see, by slowly training, we can see after some. Let's start it over. So after some 20 epochs only, 25 epochs only, we can see a distinct line separating these data points. So you can have you can go through these different data distributions available and start training your models. So here you can see there are different tabs available for us. So here there is on learning rate. This is the learning rate that we saw. While each update we take the current weight plus learning rate into the gradient accumulated gradient. So this activation function is the non-linearity that we assign after each perceptron has done the summation. So you can use ReLU, you can use tanh, you can use sigmoid, or you can use the linear. So linear doesn't do anything. It is the same as linear regression. Generally, we use ReLU as the most popular. Regularization is L1 or L2 regularization that we previously saw. How are we calculating the cost? Is it the squared difference or just the normal difference? Regularization rate is something that you can use when you want to only apply this regularization for only certain values. This we generally use it for everyone, so we'll keep it as 0. And type of classification problem, it can be classification problem or regression problem. So regression problem is a continuous value prediction. So it has to predict a continuous value between -1 to 1. So let's take a classification problem. This seems to be a good example. Let's have some neurons and some different data features also. Some sign of the data value, and we can add a number of features. So we can add some things like this, and we can start training. So here you can see the train loss and test loss. So slowly, both of them are almost following the same path, right? So that means the data that we are testing on and the data we are training on are almost the similar thing. So for example, let's use this. So there is almost no distinction between the train loss and test loss. So both of them are following the same trajectory. This is a very good training strategy. If we remove, let's see. This is also dividing it into very good values. You can go here and play with different kind of data available. Let's take some time to look into different kind of training strategies. So what is the training strategy means? So we saw gradient descent, right? So let's use this. So we have some data available for us. Let's say these are all the data points that we have, and these are the features that we have. So each column will be a feature x1, x2. So this will be x1, x2, x3, so on. So each entry here will be our each data entry. And if it is a supervised class, we'll have a label for each data point. If you don't, this is not a supervised class, we'll not have this y value. So previously we saw that we'll after doing after we sent this data, we'll get a prediction y dash for each entry. Now we'll do a summation for all these y dash minus y whole squared, and we'll get the cost function c cost c. Then we'll send it into our weight updates. W new equal to W current plus alpha of this accumulated uh, cost, right? So rather, this is called stochastic gradient descent. So since we are going through all the data and trying to update our weights, rather than doing that, we can let's take two values, and we found out y dash for those two values. We'll add those both up, and we'll use that in place of this c. So then we update some our weight, and using this we'll predict for the next two values, and using that we'll do the next update to W2. Using that new weight, we'll work on the new data. So rather than going through whole data and then updating weight once, we'll just go through some part of the data and update our weight. So here there are like roughly 6 to 8 data entry points. In real life, there will be some millions of data entry points, and it takes a lot of time to go through all of the data and just to change this weight once. So if we go through all the data and try to change the weight, it is called stochastic gradient descent. If we go through a small batch and then update it, this is called a mini batch gradient descent. So we are just going through a part of the data, updating our weights, and then going to the rest of the data, again update. So we divide our data into different batches, and we'll try to update our weights while we cross each batch. So, so what happens is, say this is our loss surface. So if we have normal stochastic gradient descent, we'll jump like this. We'll go like this. So we'll finally reach this point. Rather than this will be very stochastic, means very chaotic or very unpredictable. If we do this mini batch, what happens is it will slowly uh, go like this, and it will converge to the uh, minimum very a bit faster. So this is one of the properties of doing this weight update constantly. Say suppose we went through the whole data 5 times. So our weights have changed 5 times using stochastic SGD. Similarly, if we there are say some 10,000 uh, t- data entry points here, and we take a batch of 1,000. So and if we go through this data using these 1,000 batches, only one pass to the data, our weights will be updated 10 times, right? After each batch, we will be updating our weights. So going through all the data 5 times, we have uh, changed our weights 5 times, updated our weights 5 times using SGD. In mini batch, this batch gradient descent, what happened is within only one pass of the data, we have changed our weights 10 times. So this will help to converge our weights to the local minimum a bit faster. So if we do the same number of epochs, so one epoch is the model has seen the total training data available once. So if we go through the whole data 5 times, we have gone through 5 epochs. So in one mini batch gradient descent, batch gradient descent, if we have 10,000 and 1,000 per batch, we have updated the weight 10 times in one epoch. In stochastic gradient descent, in one epoch, we have updated our weights only once. So number of updates to the weight will increase if we are using uh, batch gradient descent. There are different other type of gradient descents available for us, namely ADAM, adaptive momentum gradient descent, and ADA and different other things. We generally use stochastic gradient descent. So we saw here, the things we saw here are, yeah. So we can take our data, we send it into neurons. This neuron will take the data, multiply each weight with the corresponding input. We'll do a summation with all the data, and we'll send it into a non-linearity. This is per neuron. So we have vertical stack of neurons available for us. These vertical stack has different weights for each thing. So we have different weights as so after this sigmoid or some non-linearity, we have output available for each neuron. We'll have a summation, or we'll pass them into a new layer of neurons that will help us to convert the information into a much more a bit more richer representation. Think we can stop it for today. In the next class, we'll see different kind of neural networks, namely convolutional neural networks for images and recurrent neural networks for time series. So convolutional neural network is for spatial data, recurrent neural networks is for temporal data.